So I'd like to welcome you to the AMATIC 2016 webinar series. Our webinar today is Teaching Introductory Statistics with Simulation-Based Inference with Allan, Rossman, and Beth Chance. And I want to let you know that this presentation is sponsored by the, I goofed that up. This is the Statistics Committee, and I goofed up that slide. I apologize for that. AMATIC is the American Mathematical Association of Two-Year Colleges, and one of our core values is building expertise and exhibiting leadership in the teaching and learning of mathematics, enhancing personal growth, and improving teaching methods and effectiveness as a personally initiated lifelong responsibility. If you want more information, you can always go to amatic.org. Please note that the views expressed by the presenter are not necessarily the views of AMATIC. Commercial products mentioned by the presenters are not endorsed by AMATIC. WebAssign is our sponsor of the webinar series. And I'd like to introduce to you our two presenters. Allan Rossman is a professor and chair of statistics at Cal Poly San Luis Obispo. He received a PhD in statistics from Carnegie Mellon University. He has served as the chief reader for the Advanced Placement Program in Statistics and a program chair for the U.S. Conference on Teaching Statistics. He is a fellow of the American Statistical Association and a recipient of the MAA's HAMO Award for Distinguished Teaching. He has given presentations and conducted workshops on teaching statistics in 37 states and 11 countries. He conducts interviews with statistics educators for the Journal of Statistics Education. I'd also like to introduce to you Beth Chance. Beth Chance is a professor of statistics at Cal Poly San Luis Obispo. Her PhD is in operations research with a concentration in statistics from Cornell University. Her research is in evaluating the effectiveness of technology on students' learning of statistical concepts and also assessment techniques in statistics education. She was assistant editor of the Statistics Education Research Journal from 2006 to 2013 and was a member of the AP Statistics Development Committee from 2002 to 2006. She is a fellow of the American Statistical Association and a recipient of the ASA's Waller Education Award and the Mu Sigma Rho Statistical Education Award. I'm going to go ahead and turn this webinar over to our presenters for today.
Thank you very much, Julie. This is Allan and not Beth, if you hadn't already figured that out. Actually, Beth is teaching until the top of the hour, which is 5 minutes ago, but so she'll probably need a couple more minutes to get here. But Beth often asks me to take the lead in doing the talking, and she'll do lots of the behind-the-scenes work anyway. I do want to thank Julie for organizing all this and for spending some time with Beth and me on Tuesday to introduce us to the software and make sure working fine. And I want to thank all of you for giving up some of your precious time to join the webinar today. I know time is our most precious commodity, and I appreciate your spending some of your time here today with Beth and me. So with that said, why don't we go ahead and get started? So here's an outline of what we'll be talking about for the next 45 minutes or so. We are going to start with some poll questions that Julie mentioned to try to get a sense for who the audience is and what your background is and what your experience with statistics and statistics teaching is. And then we'll give you a very quick overview and some motivation behind using simulation-based methods to teach statistics, which is what we'll be talking about today. Most of our time today will be spent on the third bullet there, giving you 3 examples of how you can use activity-based methods in class to introduce students to ideas of inference through simulation-based methods. So most of our time will be on the one bullet that says 3 examples. At the end of the 3 examples, we'll highlight what we think are some advantages of this approach. We'll spend a few minutes giving some implementation suggestions and some assessment suggestions. At the end, we'll point you to some resources, and then we'll be very happy to take questions. So let's start with some poll questions. And Beth and I would like to get a sense for who the audience is today. So if Julie will put up the poll, you can click in to tell us what your teaching experience is. Thanks, Julie. Greater than 15 years is up to 50%. I thought it was going to be a plurality without a majority. Oh, it's back under a majority. This is kind of fun. So that's probably long enough if you want to close the polling, Julie. But roughly half of you have been teaching for more than 15 years. But 11% of you have only been teaching for 1 to 3 years, and a good mix in between. So let me go to the second polling slide. How many years have you been teaching statistics? And it's certainly possible that never is an answer for some of you. So there's the polling. Thank you, Julie. So it's a somewhat less experienced group with regard to teaching statistics specifically. We've got about 30% with more than 15 years experience, but we've got 5 or 6% who have never taught statistics, and 20-some% who have been doing it for less than 3 years. So thank you for that. Let me go to the next slide. Another question about you. What's your background in statistics? Perhaps you never even took a statistics course, or perhaps you took a course or two, or lots of courses, or maybe you have undergraduate or graduate degrees in statistics, or maybe you're in some other category that doesn't fit any of the above. If Julie will put up the polling slide, we'll find out. So far, nobody has absolutely no formal background. Oh, there we go. Now somebody does. But lots of you, it looks like roughly half of you have no more than several courses in statistics, and roughly 17, 18% have only had a course or two or less than that. Okay, thank you. If you want to close that one, Julie. Have you ever used simulation in teaching statistics? So never is certainly an option. Perhaps just a little bit to illustrate probability ideas. Perhaps a bit more than that to demonstrate sampling distributions. Or perhaps you use simulation a whole lot as an inference tool as well as a pedagogical demonstration. So if Julie will put up the polling slide, please. So the modal response seems to be the somewhat category, but there's lots of people in each category, and not so many, just 15% who have sort of already gone whole hog and using simulation throughout the course. Okay, thank you for that. Let me ask, I think, 2 more questions if I remember right. Here's a question about p-values. Do your students ever struggle if you ask them to explain to you what a p-value represents? You can see the options. Open the polling, please, Julie. Okay, thank you. It's a pretty even split between sometimes and always. Nobody is claiming that their students never have any difficulties with explaining what a p-value is. So we're hoping in the next 40 minutes to give you some ideas for combating that. And finally, do your students ever ask whether they want to have a large p-value or a small p-value if they're conducting their own statistical study? Is that an issue that sometimes students struggle with or ask you about? So lots of sometimes's, if sometimes is a word there. So thank you very much for asking our background questions. And now let's get to it. So a good way, I think, to describe the motivation behind what Beth and I are going to present goes back decades and decades and decades if you want to go real far back, but more recently, just a decade ago, George Cobb from Mount Holyoke College gave a wonderful set of remarks after dinner at one of the first, actually at the very first U.S. COTS, United States Conference on Teaching Statistics. And he developed his remarks into a journal article that appeared in TISE, Technology Innovations in Statistics Education, a couple of years after that. And George argued that statistics teachers have been a lot like Ptolemy. And you might wonder, as I certainly wondered at the time, what do statistics teachers have in common with Ptolemy? And George argued that Ptolemy's cosmology was needlessly complicated because he had the Earth at the center of the system. And he argues that we who teach introductory statistics make our introductory statistics course needlessly complicated. Why? Because we put the normal distribution as a model for the sampling distribution of a sample mean at the center of the curriculum, when what George argues really should be at the center of the curriculum is the core logic of inference. And he went on to argue that you can help students understand, appreciate, be able to explain and relate to the core logic of inference by emphasizing simulation-based inference. So that, in a nutshell, is the motivation behind what Beth and I have been doing for the last decade, and lots of other folks have as well, that we'll be sharing with you today. So with all that as background, let's finally get to the examples. I said that the 3 examples would be the focus of this webinar. Let's get to the first one. These are all from real studies, from journal articles you can go and read about if you care to. This first one is about pre-verbal infants. And the question, broadly speaking, is, do pre-verbal infants, 6-month-old, 10-month-old infants, do they show a preference for nice behavior over mean or naughty behavior? How in the world would a developmental psychologist study that? Well, what the researchers did was they showed 16 pre-verbal infants 2 different videos. And in a moment, I'm going to show you those videos. In fact, if Julie will give me control now, I will show you these 2 videos. So let's see if I remember how to take control of the screen. So hopefully, I think you're seeing the web page that I have up now, which is from the Infant Cognition Center at Yale University. And they have a research group that does all kinds of fascinating studies on small infants. The particular study we're talking about involved showing infants 2 videos. So let me show you the first video. There you go. So wasn't that nice? I can imagine you all with smiles on your faces and feeling good about life right now with that nice friendly helper toy helping the other toy up the hill that he or she or it was struggling to get up. You can probably imagine what the second video is going to be. Let me show you the second video. And that's the second video. I can't hear or see you, of course, but I can imagine you're hissing and booing and feeling angry at life because of the mean, naughty behavior that that second toy exhibited. So the infants watched these videos over and over again, and then the researchers gave the infants a choice. They gave them wooden cutouts of these 2 toys and observed whether the infant reached out to play with the nice toy or the mean toy. And I hope you're wondering, well, maybe the shape of the toy matters. Well, they showed different videos with sometimes the triangle shape was nice, sometimes the triangle was mean, sometimes the square was nice, sometimes the square was mean. Maybe you're wondering that maybe the color has an effect. Well, they alternated the color also. Different infants saw different colors in the nice role, different colors in the mean role. But whatever videos the infants saw, they were then given a choice as this young infant is given in this video. And the infant reaches out and chooses one of the toys to play with. So that's what this study was about. And the researchers, of course, kept track of whether the infant reached out to play with a nice toy or the mean toy. So if we can go back to the slides, please, Julie. I told Julie we'd really keep her on her toes in this webinar. So thank you. So how did it turn out? Well, it turned out that 14 out of the 16 chose the nice toy. 14 out of the 16 infants chose the helper toy and not the hinderer toy. So Beth and I ask our students, what do you think of that? Does that provide convincing evidence to you that infants have a genuine preference for the nice toy? And some of them nod their heads, some of the students do, some of them sort of shrug, some of them indicate, well, maybe, but I'm not convinced. So we often follow up by saying there's 2 possible explanations for this result, right? And eventually students will say, well, one possible explanation is infants really prefer the nice toy. There is a genuine preference, and that's why so many of them chose the nice toy. But some students are quick to point out there's a second possible explanation here. It could be just random chance. It could be that the infants have no preference at all. They're just reaching out and choosing a toy at random. And just by the luck of the draw, 14 out of the 16 happened to choose the nice toy in this study. And then we ask students, well, is there one of those 2 options that we could investigate? And it might take a little more prodding than that, but we can get students to say, well, it's not too hard to investigate the random chance explanation. We could use a simple device to simulate, there's my first use of that word, we can recreate this study with a simulation that assumes that it's nothing more than random chance going on in the infant's brains. And students are pretty quick to say we could do that by flipping a coin. So we actually hand out coins to students in the class because people don't carry coins with them anymore. At least college students don't carry coins with them. And we ask each student to flip a coin 16 times, each coin flip representing one of the 16 infants in this study. We need to decide what a heads is going to mean, what a tails is going to mean. So we might say heads means choosing the nice toy, tails means choosing the mean toy. We have each student flip the coin 16 times, keep track of the number of heads, and then they come up to the board and put a dot on a dot plot on the board representing the number of heads they got. And the whole point, of course, is to see how surprising would that observed result be. How surprising would it be to get 14 or more infants out of a group of 16 choosing the nice toy if, in fact, it was nothing more than random selections going on in the infants' brains? And Beth and I do believe strongly in starting with a tactile simulation, having students literally do something hands-on by flipping the coin themselves and putting a dot on the board representing the results of their 16 flips. But then we quickly move to technology to simulate that process more quickly and efficiently. So let me advance the slide. Well, I forgot to say what I meant to say. I get so excited about simulations, I jumped right into it. We could have taken a more mathematical approach here. We could have used a binomial probability distribution to figure out the probability of 14 or more heads and 16 flips of a fair coin. And if you have a group of math majors or students who are comfortable doing math, that's a perfectly plausible approach. But to be honest, Beth and I worry, and I think other people do too, that if you just do the calculation, it's not clear what the calculation is representing. So even in our course with math majors, we start with the tactile simulation, and then we go to the technology simulation. And then with math majors and statistics majors, we come back and do the binomial calculation. But certainly with the generic Stat 101 audience, we recommend starting with the simulation-based approach. Now that I've talked you through the literally hands-on simulation, let's go to the technology version. And there's lots and lots of online tools you can use to simulate coin flipping. Beth and I developed one many years ago that Beth has since developed into an entire suite of applets useful for simulation-based inference and lots of other things. So we'll be demonstrating our suite of applets here today. So if Julie will give me back control, please. And we'll take control of the screen again. And this time, I will leave the Yale University site and go to the site where we have this collection of applets. The URL is rossmanchance.com/isiapplets.html. And you can see the links to the various applets along the top. We're just doing inference for one proportion here. So I'll click on the one proportion applet, where we first enter the probability of heads. Well, here, the null model, let me use that term, the null model is that students are picking randomly between the two options, the nice toy or the mean toy. So the null model says it's 50-50 whether the infant chooses the nice toy. How many tosses do we want to do? I try to get students to tell me rather than I just type it in. And they've already done 16 tosses themselves with a real coin, so they know to tell me to do 16 tosses. Let me start with just one repetition, because it's kind of cute to see the coin toss on the screen there. We're getting some heads, we're getting some tails. Looks like it's about 50-50. That time we got 8 heads and 8 tails. And if I scroll down, just like students would have put a dot on the dot plot on the board, the applet puts a dot saying that we got 8 heads that time. If I do it again, we might get 8 again, or we might get a different result this time. And this time it looks like we're getting 6 heads out of 16 that time, so we've got a second dot on the dot plot. I can do it again. But at this point, students say, well, sure, that's quicker than me flipping the coin, but it's not all that much quicker. It's still going to take us all day to get up to 1,000 or 10,000 repetitions. Why do we need a large number of repetitions? Because remember the whole point here, we want to know if that observed outcome in the research study, 14 infants choosing the nice toy, is that a surprising result under the assumption of random selection? That's what we're looking for. So even if you have a class of 40 or 50 students, you don't get all that great of a sense of that from 40 or 50 sets of flips. Let me now go the whole way up to 10,000 flips. I'll do 9,997 more. And you can see it didn't take any time at all. And now we've got, I mean, you don't see literally 10,000 little dots there, but it's the equivalent of 10,000 little dots there. And you won't be surprised to see that this is a symmetric distribution. You won't be surprised to see it's centered at 8. Students aren't surprised at that either, and I think it's a nice touch to ask them about that. But to be honest, we don't care all that much about the shape of this distribution. We don't care all that much about the center of this distribution. What we care about is the variability, because what we care about is the question of whether getting 14 or more heads is a surprising outcome or not. And you can look at that, students can look at that, anybody can look at that and say, yeah, 14 heads out of 16 tosses is extremely surprising if you're flipping a fair 50-50 coin. What's that have to do with infants and whether they prefer nice over mean? Well, this says that if these infants were randomly picking a toy, it would be really surprising to end up with 14 or more choosing the nice toy out of this sample of 16 infants. If you want to make this a little more formal and quantitative, we can count how many of these 10,000 sets of 16 coin flips gave us 14 or more heads. I can just enter 14. It already says greater than or equal to. In my case, it was 24 times out of 10,000. So about 0.2% of the time did we get 14 or more heads out of 16 flips. Which means these researchers have pretty strong evidence against the hypothesis that infants were just randomly choosing a toy. In other words, the researchers have pretty strong evidence that the infants really did have a genuine preference for the nice toy over the mean toy. If you want to follow that up with the exact binomial calculation, I don't really recommend that in a typical Stat 101 course, but if you have more mathematically inclined students, there's the exact binomial calculation, which of course gives a very similar result to our simulation. But Beth and I like to think that the simulation is showing what that probability means. If you could repeat this study a very large number of times, and if infants really had no preference, only about 0.2% of the time would you get 14 or more choosing the nice toy. And then depending on how quickly you want to get into more terminology and formalism, you could introduce the word p-value here. What we're doing is approximating the p-value of this test. This binomial probability is the exact p-value of the test. And because the p-value here is very small, we have very strong evidence against the null model that infants were randomly selecting a toy. So there's example 1. That could take a whole 50-minute class period in class. We just did it in 5 or 6 minutes with you folks, I think. But I think you can imagine the student interaction and the exchange of questions and answers you could have with students. So if Julie will take us back to the slides, please. Let's see what else I wanted to say about this example. Just in case the applet interface hadn't worked, we had this slide ready to go. So how about if we go to a follow-up example? This is one of my favorites. My students get sick of hearing me say this is one of my favorites because I've been teaching for 27 years now, and so I pretty much only use my favorites at this point. I have enough favorites I can fill a whole class with my favorites pretty much. But this is a really fun one. This is about a phenomenon called facial prototyping, which roughly speaking means that psychologists conjecture that people, when they hear a name, get a visual image of the face just based on whatever, their preconceptions about what kind of face should go with that name. And vice versa, when you see a face, you get an image of what the name might be based on the face. Well, is there anything to this theory, or is that hogwash? Well, here we read a journal article that presented participants with these two faces. So I'm presenting you with those two faces. I'm going to ask you to be subjects in this little study, just like I would ask it of my students. One of those two faces goes with the name Bob. The other one goes with the name Tim. Your job in the next 15 seconds is to match a name to a face. And I'm going to ask you, Julie's going to ask you with the poll, who goes on the left, Bob on the left or Tim on the left? Yeah, great. Julie moved it out of the way so you can see the faces. Who goes on the left, Bob or Tim? Can you advance that to the Bob or Tim question, Julie? Do you have the Bob or Tim question there? Reopen? Can I reopen? There we go. There you go. Thank you. Who's on the left, Bob or Tim? Beth pointed out to me that one difference now is you can sort of see other people's answers as they come in. In class, we ask students to get their answers in mind and then raise their hand and try not to be influenced by anybody else. But looks like we're about done. If you want to close the polling there, we had 37 responses. 30 of you put Tim on the left. And to be honest, that's very, very similar to what we get in class. We often get 70 to 80 or even more % of students putting Tim on the left. Don't ask me why. I'm not a psychologist. I don't know anything about facial prototyping, but for some reason, people seem to associate Tim with the face on the left and Bob with the face on the right. But of course, what's the statistical question now? 30 out of 37, that was 80 point something %, if I remember right. Is that convincing? Does that really lead you to conclude that people do have a general tendency to put the name Tim with the face on the left? Or could that have happened by random chance? Maybe your selections were nothing more, nothing less than flipping a mental coin. Is that possible? Sure, that's possible. The question is, how surprising would it be to get so many of you putting the name Tim with the face on the left if it was nothing more than a mental coin flip? Well, we can investigate that. It's the same question as with the infants choosing the nice toy or the mean toy. So if Julie will give me control yet again, we'll go back to the applet and see how convincing the results you folks just typed in are. So let me take control of the screen. I remember how. So I don't have a polling question set up for this, but if you were students in my class, I would ask you, what do I need to change? Do I leave the 0.5 there? And the answer is yes, I leave the 0.5 there because the null model is, again, a 50-50 choice. Number of tosses is now not 16, but the number of you folks who just participated in this little poll, 37 of you. Let's go straight to 10,000 repetitions. There's the result. You can see yet again, it's only our second time, but I've been doing this a lot in class lately. Yet again, we get a distribution that looks pretty normal, and we'll come back to that later in the course. It's centered around, well, looks like around 18 or 19, not surprising, in a group of 37 when we're assuming it's a 50-50 random process. But the real question is, how surprising would it be to get results as extreme as we just got? Well, you recall we just got 30 of you out of 37 put Tim on the left. And it looks like that rarely, if ever, happened in these 10,000 repetitions. I can count. How often do we get at least 30 out there? And the answer is, in my case, 1 out of 10,000. So sure, it's possible that so many of you would have put Tim on the left, even if you were just mentally flipping coins in your head. But it's incredibly unlikely that 30 out of 37 of you would have put Tim on the left if it was nothing more than a mental coin flip. So we've got, just based on our results with 37 people, we've got pretty overwhelming evidence that more than half of all people would put the name Tim with the face on the left. So if we go back to the slides again, please, Julie. This finally completes example 1. We'll move on to example 2. You'll notice, I'm sure, that everything in this first example and a half, if you want to consider Bob and Tim a half of an example, everything there is about inference for just one proportion. And we do think that starting with inference for one proportion makes things as simple as possible for a first introduction to the idea of statistical significance and the concept of a p-value. But now let's jump ahead. Here's what I meant to say about facial prototyping, which I probably said. Let's jump ahead to when we're comparing two groups. So things become even more interesting when you talk about two group comparisons. Now you can talk about randomized experiments versus observational studies. If you're talking about a randomized experiment and you end up seeing a significant difference in the groups, you can talk about cause and effect conclusions. So there's lots of interesting things that arise when you talk about comparing two groups. So here's some data from a study that Beth and I have been using and talking about for many years now. This is a study done on depression patients. And the question is, does swimming with dolphins actually provide therapeutic benefit to patients who suffer from mild to moderate depression? So we don't have enough time to talk about how the subjects were recruited and things like that, but the bottom line is 30 subjects were sent to Honduras for a couple of weeks. Half of them were randomly assigned to swim with dolphins every day. The other half were randomly assigned to the control group, So they did not get to swim with dolphins, but they got to enjoy everything else there was to enjoy with their 2 weeks in Honduras. And the researchers used a standard scale of measuring severity of depression symptoms at the beginning of the study and then at the end of the study. And they kept track of which subjects showed substantial improvement in their depression symptoms. And you can see the results on the screen there. 2/3 of the patients who swam with dolphins experienced substantial improvement. Only 1/5 of the patients in the control group experienced substantial improvement. So the obvious question the researchers had in mind behind this whole study was, is dolphin therapy effective for combating depression symptoms? In particular, is it more effective than the placebo group, the control group? So where do we start? Well, we can start by saying, yeah, 2/3 is bigger than 1/5, and it seems like by a pretty good amount. So that certainly suggests that maybe dolphin therapy is effective. But then we ask students, is there another possible explanation here? And students are pretty quick to respond. It could be random chance. Notice, though, that what we mean by random chance here is different than what we meant by random chance in the first example. Here, where was the randomness in this study? The randomness was in randomly assigning subjects to groups. So the question now is, how surprising would it be to end up with a difference between the groups at least this big in favor of the dolphin group, if in fact there was nothing more than random assignment going on here? If in fact the dolphin therapy was no more effective, no less effective than just going to Honduras, how surprising would it be to see such a big difference in the groups in favor of the dolphin therapy? And you won't be surprised to hear we're going to suggest you can explore that with simulation. But this time I am going to remember to present some other ways we could explore that first. And first of all, let me emphasize the core question of inference is essentially the same as with the infants. Is such an extreme difference unlikely to occur by chance alone? Or by chance we mean by random assignment. By alone we mean if there were no effect of swimming with dolphins. So how could you explore this? I already gave away my answer. You knew my answer from the title of the presentation. But some other approaches are, you might think that you could do a 2-sample z-test. You might think you could do a chi-square test. One problem there is the sample sizes here are so small that the normal approximation is not going to be very accurate. The chi-square approximation is not going to be very accurate. So even if you've already introduced those things, that's not a great idea here. You might be thinking more mathematically. You might be thinking we could do Fisher's exact test. If you haven't heard of that phrase, don't worry about it. But Fisher's exact test involves what's called the hypergeometric probability distribution. And that does enable you to calculate an exact p-value in this example. Just like you could have used the binomial distribution in example 1, you could use Fisher's test in example 2. But that involves a lot of mathematical startup. And I don't recommend going there with typical Stat 101 students. Again, even with our math and stat majors, we start with simulation and then follow up by introducing that mathematical startup. Kind of weird to call it startup when it's a follow-up, but that's the way we approach it. So what are we going to do? We're going to go to simulation. We're going to simulate the random assignment process many, many, many times under the assumption that those 13 subjects who improved were going to improve no matter which group they'd been assigned to. And those 17 who did not improve, we're going to assume they were not going to improve no matter which group they had been assigned to. In other words, we're assuming the null model again. Just like with the infants, we're assuming there's no effect going on here. We'll repeat the simulation a large number of times. We'll keep track of, well, that's an interesting question. You need to keep track of some statistic. One possibility is just keep track of the number of improvers randomly assigned to the dolphin group. Another possibility is look at the difference in the success proportions. We had 2/3 successes in the dolphin group, 0.667 roughly. We had 1/5 successes in the control group, 0.2. So that difference is 0.467 roughly. So we could have students calculate for each new random assignment what's the new simulated difference in success proportions, and how often do we get that to be as big as 0.467. So if Julie will give me control again, we'll go to an applet that simulates this. Yeah, we do start with a tactile. Beth reminded me we start with tactile. Again, we can't flip coins this time, but we give students 30 cards each. Some of the cards are one color to represent improvers, The other cards are the other color to represent non-improvers. So students shuffle the 30 cards, randomly deal out 15 into each of two groups, and count how many improvers in each group, calculate the difference in success proportions. See, again, we think tactile is very important to start with, but then we go to the applet, 2 proportions this time. And this one is pre-set up for the Dolphin study. If you have your own study, you can just enter your own results there and say use table. You can choose what statistic you want to look at. We're going to look at the difference in the success proportions, which was 0.467. Notice the applet also gives you a segmented bar graph of the data. That's a nice touch. You can even choose which of the categories you want to consider success. Here, of course, it makes sense to consider improvement as success, so that's what we'll stick with. But then when you want to do the simulation analysis, you can click on Show Shuffle Options. There's the 30 cards, just like students would have gotten. We try to make the applet mirror what the students do by hand as much as possible. And then we shuffle up those 30 cards and redistribute 15 to each group. And that time, it looks like the difference in success proportions was 0.2. We can do it again. That time we got something a little different. Do it again. You can even change what appears. If you don't want to see the cards being shuffled, you can go to the data list. Here it's set up like a spreadsheet. We've got the 30 results for the explanatory variable and for the response variable. And when I click on Shuffle Now, it shuffles up the response variable. It shuffles up the 30 responses and redistributes them. It's kind of subtle to see, but you can see the successes and failures getting mixed up there. Or if you prefer, and we recommend showing all 3 of these, you can show the graph, show the segmented bar graph. As I keep doing new shuffles, sometimes it doesn't change because you get the same result twice in a row, but in general it changes from shuffle to shuffle, from repetition to repetition. So that was kind of cute, I think. Now I've done 30 of them. Let me do 997 more to get up to 1,000. I'm not sure why it went above 1,000, but don't worry about that. So now we have this graph. A graph of what? A graph of our simulated difference in success proportions under the assumption that there's no effect of swimming with dolphins. What do we care about? We could talk about the shape. It looks sort of kind of symmetric, almost mound-shaped, but we don't really care. We could talk about the center. The center seems to be close to 0. So that's nice. That's how it should have turned out because we're assuming neither treatment is better than the other. So it makes sense that these results are centered around 0. But what we really care about is variability. We really care about how often do we get results as extreme as the researchers got. What did the researchers get? They got 0.467 in their actual study. So let's count how often our simulation produced a difference in success proportions of 0.467 or more. And the answer is about 1% of the time, a little bit less than 1% of the time. Once again, that's our approximation to the p-value of this test. Once again, that means if there were no effect of dolphin therapy, there'd be about a 1% chance of getting results as favorable to dolphin therapy as the researchers got in their study. Because 1% is pretty unlikely, that means we've got pretty strong evidence against the random chance hypothesis in favor of the dolphin therapy really is better than the control group hypothesis. So Julie, if you can go back to the slides again, please. I know I'm talking too much, so I'm going to need to go more quickly through the next few slides, I think. But what we try to impress upon students is that was the same reasoning process as with the infants. The situation is harder. We've got 2 variables. We've got 2 groups. So it's a harder situation conceptually, but it's the exact same reasoning process as with the infants. P-value means the same thing it did before. How you draw a conclusion from the p-value is the same as before. One difference is in terms of scope of conclusions. Because this was a randomized experiment, we can say more than just we've got strong evidence that dolphin therapy leads to a higher proportion of successes than control group. We can say that dolphin therapy is the cause of. We can't say that definitively, but we can say there's very strong evidence that dolphin therapy causes a higher proportion of successes than the control group. The other aspect of scope of conclusions concerns how broadly you can generalize the results And this was certainly not a random sample of depression patients, so we have to be careful about how broadly we generalize that conclusion. But hopefully the slides are just saying what I just said. Let's get to example 3. Sorry to rush, but I've been going too slowly. So example 3 is another fascinating study, another one of my favorites. The question here is about lingering effects of sleep deprivation. Lots and lots and lots of studies show that if you pull an all-nighter, you don't function as well cognitively the next day. This study said, what about 3 days later? And most students say, yeah, if I pull an all-nighter, I'm not at my best the next day, but most students think that 3 days later, they're back to normal and perfectly fine. That's what this study investigated. So they had a group of 21 volunteers. They randomly assigned 11 of them to one group, 10 of them to the other group. The sleep-deprived group was kept up all night on the first night of the study. The unrestricted sleep group got as much sleep as they wanted the first night of the study. On nights 2 and 3 of the study, everybody was allowed as much sleep as they wanted. And then after that, the researchers recorded this response variable. And I don't have time to tell you a lot about the response, but the response is the improvement in their reaction time to a visual stimulus on a computer screen. They did the visual stimulus thing at the beginning of the study and at the end of the study, and you're looking at the difference in their reaction times. So a positive value means the person reacted more quickly at the end of the study than at the beginning of the study. Anyway, just think of this as improvement scores. The top dot plot is for the people who were sleep deprived on night 1. The bottom dot plot is for people who got as much sleep as they wanted on night 1. Remember, everybody got as much sleep as they wanted on nights 2 and 3. What's the big difference here compared to the previous examples? I wish I had thought to make a polling question of that, but the big difference is now we have a quantitative response variable. The infant study, the Dolphin study, we had a categorical response, just a yes or no response. Now we've got a quantitative response. So this is in some ways a more complicated situation, but we're going to tackle it pretty much the same way. Let me give you some summary statistics. Well, there's the core question of inference, same as it's been in our previous 2 examples. We do have random assignment at play again here. You could jump right in and do a 2-sample t-test. And certainly students get to be pretty good at plugging numbers into formulas. You can look it up in the table or use your calculator or software. You get a t-statistic of 2.68, a p-value of 0.008. But our worry is that's pretty mechanical, and there doesn't necessarily have to be much understanding behind what's going on with that approach. And if you really want to be technical about it, there's a lot of assumptions you have to make for the t-distribution to be the right distribution to use here. And there's a lot of debate about what the right degrees of freedom is there. That's why I put the question mark there. So our approach, as you can imagine, is to use simulation. How do we simulate now? Well, it's a little bit different because we have a quantitative response, but we need to put those 21 subjects into the 2 groups, 11 in one group, 10 in the other group. We don't just have successes and failures now, so we can't just use different colored cards. What we could do, and students will come up with this if you give them a little bit of prodding, what we could do is use each person's response value, each person's actual improvement in reaction times, write that on an index card, 1 for each person, 21 index cards total. Shuffle up those index cards, put 10 in one group, 11 in the other group. Calculate the mean improvement score in each group and take the difference in the means. Do that a whole bunch of times and see how often you get a difference as big as in the actual study. And again, we do start with tactile with those index cards that I mentioned. Then we go to the technology. Let me ask Julie, I think for the last time, to give me control. And I'll quickly show you the applet that does this. You got to see a screen capture of it on the slide there, but the applet's awfully cute, so let me show you the applet. We'll go to means this time. Actually, we'll go to multiple means. And fortunately, I didn't test this ahead of time. Beth would have told me if it wouldn't have worked. We've got this sleep deprivation study here by default. You can see we've got one column for the explanatory variable unrestricted, sleep or sleep deprived. And then the other column for the response variable, their improvement score. There's the same pair of dot plots you saw before. We can see the descriptive statistics. We can choose our statistic. Difference in means is 15.92. We could use difference in medians. We could use the F statistic from analysis of variance. I don't have time to talk about MAD and max minus min, but there's other statistics we could use. The obvious choice is difference in averages, difference in means. And then we can shuffle. And you can imagine what's going to happen when we shuffle. Now you can see it better. It's shuffling up those response scores, the improvement scores. Each time it does that, it calculates the difference in sample means, the difference in group means, and plots it on the plot there. Or you can watch the graph. This is what I think is really cute. You can see the red and black getting mixed up. The red and black indicate which group the person was in the actual study. But of course, when you do the simulation, you're re-randomizing them and mixing them all up again. And you can see the difference in sample means accumulating there. So let me do 1,000 more to get to a big number. And there you have it. And now you can see, boy, that really does look pretty mound-shaped and unimodal and symmetric. And it is centered very close to 0, as you would expect. What we care about is how often did we get a difference as big as in the actual study, 15.92 or more. If I enter anything other than 15.92, it's going to say, did you really mean to enter that? I can calculate it if you want, but you might want to rethink whether that's really what you want. Happened about, well, again, less than 1% of the time. So again, the observed result would be unlikely to happen by random chance alone if there were no effect of the sleep deprivation. Therefore, we have strong evidence that there is an effect, a negative effect of the sleep deprivation. And I can use the word effect thoughtfully there because it was a randomized experiment, so it's legitimate based on the small p-value to draw a cause and effect conclusion. So let me ask Joy to take us back to the slides. And I'll have to rush through the next few slides. Sorry for my poor time management here. Some advantages of this approach. You can do it from the beginning of the course. You could literally do the helper-hinderer example on day 1 of the course or on week 1 of the course if you care to. And several of us here at Cal Poly do that in week 1 or a comparable activity in week 1. And what's important there, Beth is reminding me, is that you're not getting into the terminology of null hypothesis and significance level and p-value. You're getting at the logic of inference. And we like to think that this approach emphasizes the entire process of conducting statistical investigations. You can talk about collecting data, drawing graphs of the data, and even drawing conclusions, inferential conclusions from the data, all in week 1. Other advantages. We like to think, and there's some evidence to believe, that this approach leads students to a deeper understanding of important concepts such as significance, p-value. We didn't talk about confidence intervals today, but you can approach them from a simulation perspective. And one big plus, we think, is this is a very powerful tool. Simulation-based inference is a very powerful tool, an easily generalized tool. If you'd rather work with medians instead of means, that's a trivial change. You just look at the difference in medians instead of the difference in means. If you'd like to work with the odds ratio instead of the difference in success proportions, it's a really small change to make in the simulation-based approach. You can generalize this to more than 2 groups in a straightforward way without needing to introduce things like F distributions or chi-square distributions. If you're wondering what about normal methods, we do still encourage people to teach normal-based methods in the intro course because students are likely to see them in other places. And you'll keep seeing that normal-looking distribution show up time and time again for the simulation results. But we like to think that the normal-based approach should be encountered after the simulation-based approach. When students already have some understanding of the ideas from the simulation, then we think it's not such a big leap to introduce the normal-based methods. What about interval estimation? As I say, you could introduce confidence intervals through a simulation-based approach. Test a whole bunch of values and see which ones you reject and which ones you don't reject. Or you could use that simulated sampling distribution to estimate the standard deviation of the statistic, and then just use statistic plus or minus 2 standard deviations of the statistic as a reasonable confidence interval. If the distribution looked relatively symmetric, and you can get into details if you care to. I think this is probably the most important thing I want to say in what little time is left to me. Can you introduce these ideas gradually? And we think the answer is definitely yes. If you say you can only spare 1 class period to use this kind of thing, I would say take the first class period before you introduce p-values and use something like the infant or hinderer example activity to introduce students to the logic, the reasoning, the idea of significance and a p-value. If you can afford to devote 2 class periods to this, I would say do that plus the Dolphin therapy activity when you first get to inference comparing 2 groups. If you can afford 3 class periods, throw in sleep deprivation when you first get to a 2-sample t-test. If you can afford 4 class periods when you first get to inference regression, do a simulation-based approach to correlation and regression. If you can afford to redo your entire course, that's great too, but that's probably less common. We do have some slides about simulation, but we don't have time to talk about them, but they'll be there for you to look at later if you care to. And I do want to say a couple of things about, let me skip over conclusions, that's what I've been saying all along. There are lots and lots of resources. Lots and lots might be a little too strong, but there are coming into play many resources for doing this kind of thing. Beth and I are part of a group led by Nathan Tintle that has developed the textbook on the left. Robin Locke and his family have developed the textbook on the right, both of which take a simulation-based approach throughout the course, in addition to more traditional methods. Josh Tabor and Chris Franklin have written a wonderful book aimed at high school students, but also appropriate for college students that emphasizes sports applications. The folks at the University of Minnesota have developed a course and a book product that adopt this philosophy as well. There's a blog that our colleagues and Beth and I have developed where you can go and read articles and descriptions and comments about how to teach with simulation-based inference. The applets that I've been showing you, there's the address. The Locke group has a wonderful collection of applets and apps also. There's the address for that. So I do apologize for mismanaging time and only leaving 5 or 6 minutes for questions here, but we'll be happy to take your questions.
One of the things that I saw in the chat window is people were wondering how you actually use the applets for your class.
It varies a lot. Some of our classes are taught in a computer lab, and so the instructor will have students using the applets in class. Other classes are taught in a more traditional classroom where we do have computer projection. I'm teaching a class this quarter in such a room, so I project the use of the applets, and then students use the applets for homework assignments. So we use both of those extremes. And these applets do run on tablets and smartphones also. So even in a non-computer lab, you might have some students able to use the applets depending on what devices they bring to class, if any.
So two questions just popped up. One was, how do you test without computer access during exams?
I mean, one reaction there is you can ask students things like, what would you input? So for instance, if I hadn't done Bob and Tim with students, I might describe the Bob and Tim study on an exam and say, in order to conduct a simulation analysis, what would you input for the probability of success? What would you input for the sample size? What would you input for the number of repetitions? And then I might show them a screen capture of the results of the simulation, the graph, and ask them to show me, perhaps by circling the region, perhaps in a sentence or two, show me how you would go about determining the approximate p-value from this graph, and then make a guess for what that p-value is based on the graph. And then perhaps most importantly, explain to me in common language what that p-value represents and describe the conclusion you would draw from it. Yeah, sometimes Beth is saying we give several graphs and say which of these is the right graph, which of these would be a reasonable graph for the simulation results. Or maybe one of them you have centered at the wrong place, maybe another you have way too much variability or way too little variability.
Okay, another question was how can you guide students to use the applets in an online course? And I don't know if this applies to either of you or not, or if you can speak to that.
Beth has taught some hybrid and online courses, so let me ask her to come over. And
the other option Allan didn't mention is I usually go 1 day a week into a computer classroom, or maybe 2, and then we're working on the applets together in a more self-guided activity, and then those labs are ones I've used in the online course as well. So the applets are kind of integrated into these web pages with instructions on how to use them, and then students just take screen captures of the applet output and put that into a Word file, and they submit a lab report online.
And if you email Beth, she can point you to some of those products.
Okay. Another question came in about AP statistics. It says, how will this approach influence actual AP statistics examinations? I don't know if you have any insight to that or not.
Oh, I don't know that I have insight into that. I can ramble a little bit. I mean, the AP exam from its beginning in the mid 1990s has aimed to, and I think done a pretty good job at, emphasizing concepts of statistical inference. And the AP syllabus from the very beginning 20 years ago has emphasized using simulation to investigate and study probability. And I think more and more as time goes on, more and more AP teachers are using simulation-based methods to introduce concepts of inference as well. And those of you who are AP teachers, you know that there have been many questions on the exam over the years that present students with simulation results and ask them to draw appropriate conclusions from the simulation results. And frankly, those are often challenging questions, in part because it's much more typical to introduce the normal-based methods first and to use simulations on the sides. And Beth and I and others are advocating putting simulation more foremost in the curriculum. As to whether this will influence the AP curriculum and exam down the line, I wouldn't be surprised, but it's still too early to tell, I would say.
Okay, I did want to apologize before I stopped recording for goofing up the poll a little earlier. I didn't even realize it was the wrong one until you said, "Can you switch them?" So I did want to apologize for that. If the participants could hang on, we do have a little bit of business yet with the. I've got a. I'm trying to look. Let's see a little bit more information for you today. So I wanted to thank Allan and Beth for giving this great webinar today. If everyone could thank them in the chat window, I'd appreciate it. Thanks for participating. If you want to find out more about AMATIC, please check out bit.ly/join AMATIC. We are on Facebook. Check us out. You can get new information, up-to-date stuff on the social media site there. Recordings of past AMATIC webinars, bit.ly/AMATIC/webinars. This one, it usually takes about a week to two to produce and upload the recording from today, so give us a little bit of time for that. We've got a 2-minute survey. If you could click on the link there, the bit.ly/AMATIC45, if you could do a little review of the webinar today, it would be greatly appreciated. And thank you very much, Allan and Beth, for your time today.
Thank you, Julie, for hosting, and thanks everyone for being here with us. Feel free to send us email with questions.